So for those who don't know, so I'm Tallat, and this is my PhD defense. And I have Seif as my supervisor, and then Ali as my co-supervisor. So Ali is not here at the moment. Right, so what I'm going to do is I'm quickly going to give you an introduction of structured overlays. Then I'm going to talk about the contributions, and then I'm going to conclude the talk. Right, so what is an overlay? Basically what you have is that on the internet you have many computers connected to each other through the switches or whatever. They can route messages to from one another. On top of this, what we have is something we call overlay. This is like kind of, you can think about them as processes running on the machines on the internet. So you can start multiple of them on one machine or one of them. It's just kind of a logical abstraction on top of this machine. So in this thesis or in this talk also, I'll just call this a node basically, which is on the overlay level. And then on the overlay level, nodes are just connected to each other. They have routing pointer, just like on the internet. You can send messages over the network. Here, nodes, they just view each other on the overlay level. They don't know what is going on the physical level. Just logically, for example, this node 1 knows that it has a neighbor, which is 2, which he can send a message to. But in reality, when one sends the message, it actually goes through the physical network. So it is going to be routed through all the switches and whatever is underneath, and then it will be delivered. But this we don't worry about on the overlay level. And then this is just for routing. Then you have to use the overlay for something, right? So one of the applications is to use it for storing data. So each of these nodes can then store some of the data. So this we call the routing level of the overlay, and then we call the data level. But you can use it for other purposes as well. But for this thesis, we use it for data storage. Right. So this was overlays. Then comes in what is a structured overlay. So structured overlay, they're kind of a lookup service, which is large scale. So you can have thousands and thousands of nodes, and it will give you a lookup service on top of that. What this lookup service does is that it maps keys to nodes basically. And then once you get a mapping like this, you can then use that node for, let's say, data storage or processing or whatever. In our context, we are talking about data only. So for example, let's say these are thousands of machines. And then you want to look up, let's say, key 1. The structured overlay will tell you, this is the node that it maps to. Similarly, you can have other keys that will map to different nodes. So this is a simple example, like if you want to build a storage system on top of these of a structured overlay. For example, in this example, I'm showing, let's say you want to build a distributed DNS where you want to store domain names and their IPs as the values. You can use this structured overlay for that. Let's say, in this case, all you need to do is, like, if you want to put a key and a value, all you need to do is that you need to make a lookup for that key. The structured overlay will tell you which node is responsible for this key. You go ahead and then you save this value at that particular node. Similarly, you can put many values here. When you want to retrieve that value, all you have to do is that, fine, I know the key. What is the value for it? You again go and make a lookup for that key. The lookup will tell you which node it is stored on, and you just read the value from there. Right, so now, first we saw what overlays are, then we see a specific case, which is the structured overlays. Within structured overlays, then there are also different kinds. But the one that we focus on is ring structured overlays, basically. These are most popular, like they are most widely used. That's why we focus mainly on these. So I'll quickly tell you what ring-based structured overlays are. So these are nodes that are in the system. Many of them, they are connected to each other through the underlying network. Then, now we want to build a structured overlay on top of it. So remember, overlays are something virtual. They're not physically there. It's just a virtual presence of it. So we begin by building. We first define a large integer. This can be like more than a million. For this particular example, I'm just using 64. And you can perceive this. We call this as the identifier space. And then we perceive this as a virtual ring, which starts from 0, increases clockwise, and it ends at n-1. So that's why it's called a ring overlay, because it kind of has the shape of a ring. Now, this identifier space is mapped to nodes. How? Each node can pick an identifier from this. All you need to do is that this identifier should be unique. and they can be assigned uniformly at random or to an administrator or whatever, but usually they are done uniformly at random. Now the values that you get here are actually somewhere on the ring, right? So what happens is that virtually you can perceive all of this as if there is a ring and these nodes are placed on the ring. Now based on this ring, nodes maintain routing pointers. As we said that you need routing pointers in the overlay level. So this maintenance of routing tables is basically what Core does. So it is one of the most popular ring-based structured overlays. It has an algorithm for maintaining these pointers. And this thesis basically focuses on ring-based overlays, but most of the algorithms, they are given in the context of Core, basically. So they're built on top of Core. They use Core, almost all of the algorithms. Right, so I'll just give some of the definitions which Peter already used. So I'll just quickly go through them for those who don't already know them, who are not from this field. So first of all, the important concept is the successor of a node, which is basically the first node that you meet going clockwise from that particular node. For example, in this particular case, let's say we look at node 16. This is successor of 16 is basically the first node that will be going towards the clockwise, which is 22. So now 16 will maintain a pointer to 22, basically. Similarly, predecessor is the one that you encounter when you go anti-clockwise. In this case, let's say 22, the predecessor is basically 16. So now these are for the nodes. Then you have the similar concept for identifiers. For example, this node has identifier 26. This has 31. But then there are a lot of identifiers in between here, which can be mapped for keys, basically. So we define the successor of an identifier to be the first node that you meet going clockwise. So for example, all these keys that are there, all the identifiers from 4 to 12, the successor of all that keys is basically 12. And this we call a responsibility. We say that 12 is responsible for all the keys from 4 to 12. For example, 7 lies somewhere here, so the successor of 7 is 12, so 12 is responsible for 7. Similarly, for 12, the node itself is responsible for that identifier. Now when you make a lookup, what the lookup does is that it tries to find the node that is responsible for that particular identifier. For example, if you make a lookup for 7, you will get routed, and you should get, like 7 is here, responsible is 12. So the lookup should return you that node 12 is what is responsible for this identifier. Right, so this is just background stuff. Now I'll quickly go through some of the contribution I made, and then some of them I'll go into more detail. So as I said in the beginning, for overlays, there is the routing level, and then there's the data level. There were some contributions we made on the routing level and some on the data level. For the routing level, I'm going to talk more about the problems that we solved, why they were important, and what we did about them. I'm not going to go into details of how we solved them. Peter already covered some of them. Some of them were covered in the essentials. So here I'll just give an overview of those. On the data level, I will go a bit more into the detail, like what the problems are and how exactly we solve them. Right, so let's begin with contribution on the routing level. So we saw there's an underlay, there's overlay. Now, as Peter pointed out, there can be network partitions. Like you cannot avoid network partitions in a distributed system. They are going to happen. Now or later, you have to deal with them. So for now, so this overlay basically it kind of looks like a rectangle, but it's actually you can imagine it as a ring, which goes from here like this round. So now you have the underlay, you have the overlay on top of it, the network partitions. As soon as the network partitions, the nodes on this side cannot communicate with nodes on the right side. So all these links that cross these partitions, for example, if this node wanted to send a message here, it had to go through this particular link, and that link is now down. So that message cannot reach here. What is nice about periodic serialization of Core and many other structured overlays is that as soon as they detect these failures, they are going to fix the structured overlay. So what happens is that after a while, nodes will detect the failures, and they will create separate overlays. So you will end up with a separate ring over here, separate ring over here, in this partition as well as that partition. But someone is going to notice that there was a partition, is going to fix it, or if it's an autonomous system, the partition will eventually be fixed. Right. So what happens then is that even though the network is fine now, the overlays still remains separate. Like, what ideally we want is that once the partition heals, we should also merge the overlays into one. So this was our first contribution. We call it ring unification. It is so we give an idea of how you can detect network partition mergers, and we give an algorithm which you can use to merge multiple overlays into one. Such an algorithm can be triggered by this mechanism here, or it can be an administrator, or whatever the scenario is. So the properties of this algorithm basically are that it provides some parameters that you can use to tune it so that you can have a trade-off between the bandwidth consumption and the time completed to merge multiple overlays. So as Peter showed one graph, like if you want to quickly merge two overlays, then your bandwidth consumption will be very high. But you can do that using some particular parameters here. If you don't want to use a lot of bandwidth, it will take more time to merge. Similarly, we make this algorithm so that it's lean. If, let's say, there are thousands of nodes, and then some node wrongly detects that there was a partition, and now it wants to merge, but actually there was no partition and merger. So what we want to do was we don't want to send a lot of messages out there when there was actually no merger. So we try to make it like low cost if there was no actual merger. And this is a terminating algorithm. You start it when you want to merge. After a while, when they are merged, the messages die out and the algorithm terminates. This is just a quick simulation where, let's say, we start with two rings. We start the merger by detecting one node from one ring to another in the other ring. We start it, and then the algorithm basically fixes itself. So the red nodes are in one overlay, the blue are in the other, and all of a sudden they try to fix the overlay into one. So it's kind of the same as what the figure that Peter showed. Is just animated, basically, to show what's actually happening. And this is just simulation time. It's not real time. Like, it's not actually taking this much time. Right. So eventually it merges into one. So this was the first contribution. Second, what happens with overlays is that they have a limit at the rate at which nodes can join the system. When you have such a limitation, then it becomes slow to bootstrap a large overlay. So let's say you want to start a network with thousands of nodes. Then you have to all of a sudden have to wait for the initial nodes to join. Then you join more. Then you join more. So it can take hours to basically bootstrap an overlay. But this problem in itself is important. People want to do that. So there are certain algorithms for bootstrapping an overlay. The problem usually with them is that they are separate than the maintenance algorithm. So what they do is that they first bootstrap into an overlay, and then they have to detect that the bootstrap has finished. Then they have to hand over the overlay to the maintenance algorithm, which is kind of becomes a bit complicated in such cases. So this is the problem. Like, what does bootstrapping mean? So all these algorithms that do bootstrapping, they assume that you start off with a randomly connected overlay, and you want to build a ring structured overlay, let's say. So what you can do is start with this, run the bootstrapping algorithm. It will converge into one ring. So this brings us to the second contribution of the thesis, which Peter just pointed out as well. We call it recircle. It builds on periodic stabilization and ideas of ring unification. It joins those ideas into one algorithm. And that single algorithm, what it does is it has three nice properties. Like, it does efficient and scalable bootstrapping. It also does overlay maintenance, as it borrows from periodic stabilization. It also handles network partitions and mergers, which it borrows from unification. So now we give you one algorithm which does everything that overlays were supposed to do. So as a user who implements this, they don't have to worry about multiple algorithms or how one algorithm can affect the other. Like, as you mentioned, like in cats, we didn't have to worry about such stuff. It was already. So of course we have to worry on the data level, but on the routing level, we take care of these things. So this is what like overlays were supposed to do. Like, they did a lot, but just we kind of converge into one final thing. This is the same, like you start off with a randomly connected nodes, and then you start your algorithm for bootstrapping. Red nodes mean that their successor predecessor pointers are still wrong. The green ones are the ones that have already the correct successor predecessor pointers. So the system kind of evolves over time, takes a structure. Again, this is just simulation time, like I'm pausing it to give you a view of what's happening. In reality, it goes much faster than that. So after a while, nodes keep on running the algorithm to converge into a ring eventually. Right. So that's recircle for us. Under normal circumstances, it just behaves like a normal maintenance algorithm, which is periodic serialization in our case. It's only under extreme events like bootstrapping or partition mergers that it sends extra messages. And that's exactly what we want. We don't want, because partition and mergers, they are not events that occur very often. They just occur once in a while. So we don't want to be sending extra messages just because of an event that happens once in a while. So we designed recircle such that it just reacts to when these events happen, and then it sends extra messages. For example, in this simulation, the x-axis, let's say, is time. It's time. The y-axis is the bandwidth that peers are using at that particular time. So as we go here, everything is fine. It's like normal periodic serialization bandwidth. Now, at this point, we start a merger of multiple overlays. The algorithm detects that. It starts sending extra messages to quickly merge those overlays into one. As soon as it's done merging them, those extra messages start dropping out, and eventually you get to the same level as you were before you started this merger process. So we also experimented with this algorithm on Planet Lab. We could bootstrap 1,000 nodes within 10 seconds. We could merge 1,000 nodes within 10 seconds as well. So it's quite good. If you try to do that with only periodic serialization, it's going to take a long, long time. Next, we had the contribution of network size estimation. This I'm going to go quickly because I think Peter gave a very good overview of it. So you want to estimate the network size. This estimate is used in a lot of applications. Like in overlays, you use it, let's say, for load balancing or to tune the rate that you want to do periodic serialization and stuff like that. So what makes it more difficult is that peer-to-peer systems are completely decentralized. Like you don't have one guy who has the whole view of the system to tell you what the size is. So there were quite a few solutions for this because it's an important value to know. But then what happened is that there was a study done which showed that out of all these algorithms, there is one called Ghodsi-based aggregation, which is very accurate. It gives a very accurate estimate. But the problem with it was that it was not highly resilient to failure. So they had ways around to handle such cases, but they were not so elegant, and they had more cost associated with them. So, and then they were not directly applicable to structured overlays. They assumed that they had a random view of the system. And similarly, they require that you need to predefine the convergence time. Like you have to say that, OK, after 30 rounds of messages exchanges, whatever the value we converge to, that's the value that we have. So we gave an algorithm which we designed for structured overlays. And this is much more resilient to failures, as Peter showed in the graph. And it doesn't need to, it's kind of adaptive, so you don't need to predefine the number of rounds. You still need to say some error bounds that are acceptable to you, but still you don't need to say how many rounds you want. So of course, I mean, yeah, you have to still give an error bound for it. Right. So now we start moving towards from the routing level to the data level. So now what I'm going to talk about is problems that can happen on the routing level that can affect the data level indirectly. So we are in the context of asynchronous networks. We know that in asynchronous network, it's impossible to perfectly detect failures. So you will always have incorrect failures. So I'll just show you one of the problems that can happen due to incorrect failure detection. So let's say this is part of the overlay. And all of a sudden, 10 is a bad node. It has a bad network link or something. It thinks that 30 has failed, when in reality 30 has not failed. It's still there, but 10 thinks that it's dead. So now 10 points to 40 instead. And since we said that 10 is very bad, it also detects 40 as failed, so it's pointing to 50 as its successor. What can happen now is that imagine there's a key 35 in between, and you make a lookup for this particular key. Let's say the lookup arrives at 10. In this case, 10 will think that 50 is the responsible node, so it will return 50. But the same lookup, if it arrives at 30, this guy will think 30 knows that 40 is alive, so he will say that 40 is responsible. So basically, all these key ranges here, there are two nodes responsible for it, 40 as well as 50. And this can lead to inconsistencies in the data level, because if you want to do writes and reads for this on top of this overlay, what can happen is that when you do a write, your write might be stored at 50 or 40, depending on how your lookup is resolved. So then your next read might go to the wrong node and read an older value from there, and then you violate consistency, basically. So in this work, we studied and looked at the reasons of why lookup inconsistencies happen, and we kind of try to measure how often they happen and how they lead to data inconsistencies. We found out that inaccuracy of failure detectors is one of the main contributors compared to churn, let's say joins and failures. And we discussed some of the mechanisms that can reduce the effects of these lookup inconsistencies. And as Peter mentioned, so some of these were in the folklore, like some people talking about, you can use this way or that way to reduce. But what we want to do is, like, if you want to build a system on top of such thing, you have to first evaluate and see that actually there is such effect. So that's why we wanted to first study these, that there is something like that. Now, the problem is, like, as soon as you talk about consistency, you run into a theorem called the CAP theorem. CAP theorem basically caps, the C stands for consistency, A for availability, P for partition tolerance. So what does consistency mean? It basically gives you a set of rules that tell you what operations are permitted and what are not. For example, if you do a read operation, it should tell you that you should read the latest value. Availability means that if you do a request, you should eventually get a response for it. Partition tolerance means that even if the network is partitioned, your system should work correctly. But as we saw that partitions are going to happen, you cannot avoid them. So what we have to do is that the theorem says that you cannot have all three properties at the same time. You have to choose two of them. So partition tolerance is going to happen, so we cannot say that we just avoid to handle network partitions. So that's given. So now what you want to do is you want to choose between availability and consistency. So this completely depends on application needs. Some applications are fine with inconsistencies. They want availability all the time. But we concentrate on applications that want consistency. And they can compromise on availability. Right. So this brings us to our contributions on the data level. So on the data level, as soon as you talk about fault tolerance, you have to replicate your data, basically. Up till now, we didn't talk about replication. So if there's a failure, you still want your data to be available, you have to replicate it. What happens with replication is that now you run into the problem of keeping multiple replicas consistent, right? Now the problem here is that your system is asynchronous. You don't know if a particular node has actually failed, or is it just I'm inaccurately detecting him as failed. So you cannot be sure ever. Then there are network partitions and mergers. If there's a partition, you think that node has failed. Actually, it's just a partition. That node is still performing its actions. Then you have nodes join and failing all the time. It makes it difficult to achieve consistency. Now, in the context of distributed systems, generally people use quorum algorithms to achieve consistency among replicas, especially for just read and write operations. So for quorum algorithms to work correctly, they have a correctness condition that should be met. Only then they will work correctly. In this context, we just talk about majority-based quorums. So that's what I'm going to focus on right now, but it's the same for any quorums. So for consistency to be achieved, it's important that all the operations, they should overlap on the nodes that they are performing on. So when you pick quorums, they should always overlap. For example, if you have 3 replicas, out of 3, a majority means 2 nodes. So a quorum consists of 2 nodes. So let's say operation goes and updates these 2 nodes. Now, if you take any other quorum, it is always going to overlap with at least one of the nodes, right? So this guarantees that you will always see what other operations are doing to the system. If you have non-overlapping quorums, that's when you will violate consistency. For example, here, if you had 3 replicas, let's say, let's ignore this replica for now, and you have an operation that updates these nodes. It's a majority-based quorum. Now, if you want to do a read, and you did not pick a majority, you just pick one node, you might read from this guy. You will get an old value. So you have to, first of all, read from a quorum. But there is another problem as well. Like if there is some guy who is trying to make you think that he is also a replica of the system, but the replication degree is still 3. He is just falsely believes that he is a member here. Now, quorum is still 2, so your operation might happen here, and then you can read a stale value. So the correctness condition for quorum algorithm is that they should always, all the quorums should always overlap. So I will talk in a slide why I'm saying that. Right. So in ring overlays, now we were talking about replication. There are various ways of doing replication. For overlays, one of the most commonly used replication scheme was proposed by the court guys, and is widely used, which is called the Successor-List replication. And this is what we use in our system as well. So let's say here is the ring. You have each node is responsible for certain keys. For example, 30 is responsible for keys from 20 to 30. So all these keys, let's say from here to here, are stored on this particular node. Now you want to replicate this data. The technique that Successor-List replication uses is that it says that you need to replicate this guy on the nodes that follow you clockwise on the ring, which are kind of the successor of this node. For example, the keys from 21 to 30 are stored in that guy. That's the first replica. But then you have to copy them on the next node as well as the next node. So if your replication degree is 3, let's say, these keys with their values are stored here, here, and here. Similarly, the same case for all of the key ranges. They get copied going clockwise. This guy is replicated here, and so on. So this is how they achieve replication. So if you look closely, this guy basically has stored these keys as well as these keys as well as these keys. So now if we think about, OK, fine, we are replicating data. We have these keys that are replicated on these nodes. We want to achieve consistency. Easiest way is fine. I just told you, right? We can use quorum operations, and we will get consistency, right? So just think of these 3 nodes as, we call it a shared memory register, and just do quorum operations on these 3. We know that if we do majority quorums, they will always overlap. Life is good. Problem is that life is not so good, because we are in a asynchronous network. So what can happen here is the same. It's kind of the same concept I showed you before. Just this now. Now I'll try to show it with replication as well. So let's say 10 thinks that 30 has failed. Now these pointers I will not update here just for simplicity. The problem now is that there are 2 replication groups for the same key ranges. This guy, 30, thinks that the replication group for these keys is 30, 40, and 50 using Successor-List replication. On the other hand, 40 thought that 10 is dead. So the way he thinks of the replication is that he is responsible for this key range as well. So the replication group is 40, 50, and 60. Because he thinks that this guy is dead, so he has to be storing these keys. So he thinks that the replication group is 40, 50. Replication group is 40, 50, and 60. Looking here, you can clearly say who's the replication degree, but in an asynchronous network, nodes are completely decentralized. They don't have a full view. This is what happens. So now if you have a key 20, you do a quorum operation on it. You can have non-intersecting quorums, basically. How can you do that? So let's say if you do a put for key 20, it can contact this replication group here, and it can update, a majority is 2 nodes, it can update 30 and 40 over here. But then another operation comes in for the same key. It contacts a majority, but he thinks of the replication group as a different group, so he goes and updates 50 and 60. Now these two groups are what? Non-intersecting. As soon as you have non-intersecting quorums, you'll run into inconsistencies, basically. So what we set forward, from this example, what you saw is that non-intersecting quorums can exist if different nodes have different views of the replication group, and a node thinks that it is responsible for a particular key range when it should not have thought like that. So what we set forward to do is that we wanted to prevent such scenarios, and in certain cases, even if they happen, we want to still achieve consistency. So that's our contribution number 5, which we build a system on top of it called CATS. What we do here is that we saw that as soon as different nodes think differently of the replication group, things go bad. So how to fix it? You have to maintain the membership of the replication group consistently, which means that any changes you make in the replication group, people should agree with that. We look at what that means more. And this is just not enough. We also introduced a technique called consistent quorums for doing read and write operations. Consistent quorum, like it is the same concept as quorum, but we enhance it a bit with a particular definition, which is the following. Like a consistent quorum is a quorum of nodes that are in the same view, which means that they have the same view of the replication group. Right, what does this mean? Like I'll just show you an example of consistent quorums. So let's say these are replicas. Each replica has a view of who are the nodes in this replication group. Let's call this V. So A thinks that the view of the replication group is V, and V you can assume that it's a set which contains A, B, and C. So A thinks that A, B, and C are the replicas. B also thinks the same. He has the same view. But this replica is kind of, due to inaccurate suspicions or whatever, it thinks of the view differently. Like he thinks that, no, the view is V prime. And V prime can be anything. Like let's say he thinks that the view is B, C, and some other node D. So what happens now? We have to use consistent quorums to still provide consistency. And this is how we use it. This is what the core idea of consistent quorum is. As soon as the client wants to do an operation on quorums, it sends out requests to all the replicas that it thinks are the replicas. Every replica will reply, but it will also attach the view that they think the replication group is made of. So this replies with V. This guy replies with a V prime, because he thinks the view is V prime. There can be other data associated with it. We don't care right now. In the complete algorithm, we give what should be here as well, but this is just a high-level concept. Now, when the client gets all these replies, if majority of the replies have the same view, only then the client can say that, my operation succeeded. And this same view at the majority, we call it consistent quorums. So for example, in this particular case, majority is 2 out of 3. So these two guys replied with the attached view of V. So fine, majority has the same view V. I have a consistent quorum. So things are good. And this view V, which was in a majority, we denote it here as the consistent quorum. So whatever operation was going on is fine. It can continue. But then there are some quorum operations that do things in 2 steps, like 2 phases, like 2 round trips. So for example, if this was an operation that requires 2 phases, now we have to use consistent quorum in the second phase as well. Otherwise, you violate consistency. You can have non-overlapping. You can have different nodes that you operated on in the first view versus first phase versus the second phase. So the client has to use the consistent quorum that it got in the first phase. So next time in the second phase, when the client sends requests to the replicas, it attaches the consistent quorum that it got in the first phase. Like it says, I gathered this consistent quorum. This is what we should use for my second phase as well, because the operation is still the same. The nodes, the replicas, when they receive such a request, they check if their local view is the same as what this consistent quorum was attached in the request. If it's the same, fine, things are well and good. This replica can reply as an ACK or send back data like, yeah, things are fine. I have the same view as you. It's OK. But this guy receives the message. Remember, the consistent quorum was V. So he will try to compare it with his own view. It's not the same. So he will say, no, this is not the same as my view. This is not acceptable for me. But the client already gets an acknowledgement from a majority, so the operation completes. Everything is fine. No consistency is violated. So this is the basic idea of consistent quorums. We go into more details in the paper as well as give in the thesis as well as give correctness proof as well. But this is the high-level overview. One important thing here is that if there is another replica D, he also has a view of the system. But this view cannot be the same as V prime. Because if it were the same as V prime, then what will happen is that you can have consistent quorums with different views. So now a client can get a consistent quorum of V. Another client can come and get a consistent quorum from V prime. So these quorums are also not overlapping, and then everything goes boom. So whatever this replica has, view, it should not be V prime. How do we make sure? Well, views change. You should always do reconfiguration when views change to avoid such scenarios. What does this reconfiguration mean, basically? It means that if you want to do any changes in the replication group, they should first be proposed using consensus. So I'll not go into the details of consensus, but the idea is that you can propose values in consensus. This value can be anything. For example, we can propose what changes we want. A majority has to agree that, fine, this is what is going to happen. And then the decision is whatever a majority agrees should be. So in this particular case, let's say if you have a replication group of 1, 2, and 3, and someone proposes that I want to replace node 3 with node 4, this will be proposed through PEXs. Eventually, the decision will be, yeah, right. We can go ahead and change the replication group. So this is just a decision that you can do it. It's not happened yet. So once the decision is taken that we can change the replication group to have this particular new view, this new view is now installed on the nodes. But we have to do it carefully so that not to create multiple consistent quorums with different views. So we have to make sure that for each group there is only one view which can have a consistent quorum. So let's see how this reconfiguration occurs in practice. So we have replicas A, B, and C. They have a view V. Let's say this view is ABC. All of a sudden, a node D comes in which wants to replace node C. This is proposed through consensus. Everyone agrees that, fine, you can come, join in, and replace C. Let's say this new view is V prime, which is basically ABD, which is removing C from the group. Now it's the time to install. What happens is that first it gets installed at the old nodes. Let's say it gets installed at A. So please keep an eye that you can never have non-overlapping consistent quorums. For example, here you could get a consistent quorum with view V. At this point, still you can get a consistent quorum with view V, but you cannot get one with V prime because there is only one node which has V prime. There is no majority with V prime. Next step, it gets installed on another node. So now at this point, you can only get a consistent quorum with V prime. You cannot get one with V because it's not on a majority. So this has to be done first on the nodes that are already in the group, and then at the end, you go ahead and do it at the guy that is joining now. At this point, you can get consistent quorum with V prime, but not V anymore. Why do we need consensus? It can happen that there are multiple people that are trying to change the group at the same time. If you don't use consensus, you might end up with two different views. I'll just quickly go through an example where I show what happens when multiple nodes propose a change. So first, these two nodes, they want to make a change into this group V. But let's say we run PEXs, and PEXs has only one decision. It says, in this reconfiguration, I only allow this node to join and replace this guy here. This will have to wait because first we need to make this change. So as before, this new decision will be installed on the old nodes, and eventually on this new node here. As you can see, there are still consistent quorums of only one view at a particular time. At this point, you can go ahead and serve this guy as well. Whatever changes he wanted to make in the replication group, you can do that as well. So let's say he wants to now remove this guy from the group and wants to join instead. What happens is that this new view will be proposed through Plexus, decided, and installed on one node, then on another node in the older view. Now, this new guy, once it's installed on a majority here, you can install it on the new node. So the interesting thing to see here is that even if there are so many views, like let's say here there are 1, 2, 3 views for this group, you can have a consistent quorum for only one view, which at this point is V double prime. You cannot have a consistent quorum for V or V prime. So whenever you move to a new view, only a minority is left in the older view, so you can never get a majority for it anymore. So this is just giving you high level, because in the implementation of a real system, we need to move data. We also need to remove any stale copies that are not needed anymore. Like for example, this guy is out of the replication group. He doesn't need to store this view or the data. So we go through all those details as well in the actual implementation of the system and the thesis, but here I just give you a high level overview. So we guarantee that even if there are multiple reconfigurations going at the same time, they will be ordered, so one change will happen at a time. We also guarantee that for every replication group, 2 consistent quorums will always intersect, and operations will always terminate as long as the majority is accessible. So remember, there is still the cap theorem. So for example, if there are partitions or a majority has failed, you might have the operations might get stuck or not complete, but as soon as that condition is satisfied, the operations will terminate. So cats basically, I mean, this algorithm basically give a consistent mapping from the key ranges to who is the replication group basically. So using these ideas, we made a real implementation called CATS. This is implemented in Compix. What CATS is as a system, it gives you like a storage system for keys and values, which means that if you have a data store, you can put key against a value, and later you can retrieve it. This is the basic concept of a key value store. It is scalable. The reason it's scalable is that we use structured overlays for it. And structured overlays, we know by definition, are scalable, and they distribute the load of it of the whole system to nodes themselves. So that's why it becomes more scalable. So this data store actually is not just a single data store. It is basically composed of many machines and lots of data on top of it. So at this point, so I'll just maybe say, like, because Peter mentioned that the scalability of CATS, we tested it for 100 nodes, basically. So, so there are 2 things here. So first, the ideas that we use here, they are completely decentralized. Like, they're not depending on one server or something like that. So it's inherently scalable in that sense. Like, if you add more nodes, you are just redistributing the responsibilities between these nodes, and the responsibility of one node remains the same. So in that sense, it is incrementally scalable. The reason we experiment with only 100 nodes is that we were doing experiments on Rackspace, where we deploy the actual CATS servers, we run them. So that's like, there's a limit at which you can do the experiments on. We believe, like, the ideas here, there is no centralized dependency, so they will kind of there is no bottleneck for them not to scale. CAS is linearizable. Like, linearizability is basically strong consistency, the strongest that you can get for reads and writes. So this basically linearizability means that read and write operations are indivisible. They appear to the system as if they occurred instantaneously. For example, if you do a put here and the put succeeds, you get an OK. So now if you do a get, you should get a value that was written. If you get a different value, it can only be a value that was written after this put. It cannot be an older value, basically. So that's the basic idea of linearizability. and it's partition tolerant. So we saw that on the routing level we have recircle that can fix partitions. But also on the data level we are using PEXs and quorum algorithms which are intrinsically partition tolerant. But still the cap theorem applies. So for example, if you have all the nodes, you do a put. If it succeeds, then your get should either get that value or it should block if those machines are not accessible. So you should not get inconsistency. Right, so this is the last contribution that we have to talk about. So successor-list replication is used in a lot of systems, but it has some shortcomings, basically. So it is kind of like when churn happens, it's a bit complicated to handle it. The changes that you have to make, it's a bit more difficult to load balance it. And it's also difficult to implement replication policies like locality-based replication and things like that. Here, I'm just going to talk about what we mean by, in case of churn, it's a bit more complicated. The rest are discussed in the thesis as well. Right, so let's see what happens when you have successor-list replication and a join happens. Right, so here you have nodes. Sorry. So you have nodes, they are replicating data. For example, this guy over here is replicating this key range, and this key range. As we saw before, that's how successor-list replication works. All of a sudden, a new node joins in here. So this guy now is responsible for this range, right? So it should replicate that. It should kind of get that data and replicate it. So let's see all the changes that have to be made. First group that needs to be changed is this group 3035, which was stored here, here, and here. Now, this node is responsible for keys from 30 to 33. So these keys should basically move in here, right? From 30 to 33. At the same time, this guy here should divide this range into two, from 30 to 33, because now it's his responsibility, and from 33 to 35. Divide them into two ranges. This guy should do the same, 30 to 35. This guy should remove some keys, because now he should replicate only 3 nodes, right? So he should replicate his responsibility. What is the responsibility of this guy? What is the responsibility of this guy? This guy's responsibility was 30, 35, but it has changed now. It has become from 33 to 35. So he should remove some of the keys. He should remove keys from 3 to 33. He does not need to store them anymore. This is one group. There's another group that needs to be changed. This I'm talking with replication degree 3. Sorry. What happens to this group 2? It was replicated here, here, and here, but now there is a new node. So this replication should go here. So these keys now have to be copied here. This guy has to delete them, because now he doesn't need to store this guy anymore, because he only needs to replicate his own responsibility, another node, and another node. So he doesn't need to store this anymore. He can just delete them. Similarly, this group has also to be changed. It was stored here, here, and here. First, this has to be copied here, because now the replicas should be this guy, and this guy. And then it has to be deleted from here. So basically, I mean, if you are confused what I said on this slide, I'm very happy, because it is confusing. Like, when we were implementing this, I mean, it really gives you headaches. Like, I mean, imagine you have replication degree of 5, and you are joining 5 nodes. All of a sudden, you need more coffee, you get nightmares. It's terrible. So what happens here is basically, we saw that if on one join, there will be R groups that will be disturbed. R groups need to be changed. We saw here 1, 2, and 3. It's more complicated to debug. Like, at some point, we were doing replication degree of 5, and we had 5 churn events. So all of a sudden, we have like 25 reconfigurations to keep track of what's happening, what's not. We don't wish that on anyone, basically. So we come to fix that. This is the system we call ID-Replication. So it's a different kind of replication scheme for overlays. What the proposal we give is that basically, instead of using nodes as the building block of the overlay, we use a set of nodes as the building block. We call this set of nodes as groups. So now, previously we were partitioning the identifier space and responsibilities to nodes. Now we will assign those to groups instead. What does that mean? So this was how things looked like before. 35 was responsible for this key range. 30 was responsible for this key range. But we said we don't want to talk about nodes anymore. We want to talk about groups. So instead of one node being on the ring, we have basically a group of, let's say, 3 nodes. So each node now on the ring is replaced by a set of nodes on the ring. So in reality, these are still nodes, right? So now every node has 2 identifiers. Previously, it just had 1 identifier on the ring. Now it has 2. One is the ID of the group. The other is the ID that it has within the group. So the group IDs have to be unique, of course. But within a group, you can have IDs that are the same as another. It just has to be unique within that group to identify a particular node. So all nodes within a group have the same group ID, but they have different local group IDs. And then, of course, like it's obvious how to do replication here. Like nodes in the same group are responsible for the keys that that group is responsible for. So they act like the replicas of that particular key range. And then the size of the replication group basically defines what your replication degree is. There are some exceptions that are dealt with in the thesis I'll not talk about here. So the maintenance of these groups is the same as, it's kind of same as before. Like Core did periodic stabilization for nodes on the ring. We use the same concept, but we apply it to groups instead of rings. So nodes in one group do periodic stabilization with nodes with their successor group. And within a group, we synchronize the view of the group by gossiping with nodes within the group. This gossiping you can also use to update replicas of the nodes. But that's not, I mean, that's just a proposal. So each group now, I mean, what we do is like we have the size of the group, right? Now what we do is that we specify the size using 2 parameters, rmin and rmax, which is like the size of the group should be between rmin and rmax. We generally use the maximum to be 2 times the minimum. So now let's see what happens with churn, because previously we said that it's too complicated. So the size of a group can become less than the minimum if there are failures, right? Because the size is between the minimum and the maximum. A failure, if you already are at the minimum and the failure happens, it will become less than that. Whereas upon joins, you can exceed the maximum of a group. What we want to do is that even if there are joins and failures, we want to ensure that the size is between these bounds that we specify. So before I say how we handle those, I'll introduce a concept called standby nodes. So standby nodes are the nodes that can leave their group without violating the replication degree. For example, if you have a node, if you have a group and your rmin is, let's say, 3, and there are 2 more nodes, rmax is, let's say, 6, and there are 2 more nodes here. Even if these 2 nodes leave this group, even then the size of the group does not violate our requirements, which is it should be between rmin and rmax. So these nodes, we call them standby nodes. They can just leave this group whenever they want. They will not violate the properties. And what these nodes do is that they advertise themselves using gossiping, or there's another technique called directories. I'll not go through that. But the concept here is that you can find out who standby nodes are in the system if you want to know who they are. So now the scheme is nice because now these groups, you can easily implement replicated state machines on top of them. For those who don't know, replicated state machines, you can implement transactions within replicated state machines. They are even stronger than linearizability. You can do much more than just put and get operations. This system kind of gives you nicer ways of implementing more policies. And it turns out that if you have some configuration in successor-list replication, it can also be represented using ID replication by using virtual servers. So this is kind of what we want to prove formally. It's not in the thesis yet, but we are working on that now. So I'll conclude now. So for the thesis, I'm just going to summarize the talk and the thesis. We had some contribution on the routing level. We showed how to merge multiple overlays. We showed an algorithm that does bootstrapping, mergers, and maintenance. We showed how to estimate the network size. We talked about lookup inconsistencies, how they can arise, how can they violate data inconsistencies. We show algorithms that you can use to achieve consistency in a completely decentralized setting. We built a whole system on top of it that's deployable and usable. And we give a new replication scheme. So what we want to do is, like one of the points that Peter also mentioned, like we want to give a theoretical proof of not just a proof, but also like bounds on how many theoretically how many messages will it take, or how much time will it take to do mergers. We also want to use this concept of consistent quorum because it's very nice. It gives you a consistent view of who the membership are. So we just used it to build a key value store. We believe that you can do much more. You can build transactions on top of them, which is very strong. So that's kind of what we are looking at for future. Some of the techniques we used here, we believe that we can try them to implement them in non-ring overlays as well. We also, what we want to do is use ID-Replication to build a consistent key value store. Like CAS uses Successor-List replication, but what we want to do is use ID-Replication to make such a storage system. So that's the end of the talk. I'd definitely like to put in some acknowledgements here. I'd like to thank my supervisors, Seif and Ali, the committee member who came all the way here to do an opposition, all my colleagues at KTH and SICS. It was great, not just working with them, but it's a really nice environment as in feeling like home. Also, all my friends here in Europe. It was a really nice experience for me. Thank you very much.
Thank you, Tallat.